Good evening. Today we will see the quadrature amplitude modulation. That is, quadrature amplitude modulation is also called as quadrature amplitude shift keying. We will see the quadrature amplitude modulation transmitter and receiver for total number of symbols m is equal to 16. That is, the number of bits small n is equal to 4. Means number of symbols will be m is equal to 16. So first of all, we will see what is meant by quadrature amplitude modulation. So it is the modulation technique in which the phase as well as amplitude of the carrier changes according to the input data. It is called as quadrature amplitude modulation or quadrature amplitude shift keying. Okay, it is the also combination of 2-bit PSK and 2-bit ASK. Already we have seen the PS shift keying and amplitude shift keying. So we can also, it is known as combination of 2-bit PSK and 2-bit ASK, and in that also we have seen that QPSK and MPSK, quadrature phase shift keying, and MRAPSK. In quadrature phase shift keying and in MRAPSK, all the symbols lies on the circumference of the circle. Means the amplitude is constant and phase is varies in the QPSK and MPSK. Means in constellation diagram, if you see this bottom figure, symbol S1, S2, S3 and S4, all the symbols are lies on the circumference of the circle. Means in these two types, that is QPSK and MPSK, the amplitude is constant, only the phase is varies. But in QAM, quadrature amplitude modulation, it is not happened. In that QAM, amplitude as well as phase of the carrier changes according to the input data. This is the main basic difference between QPSK, MPSK and QAM. Okay, so this is the constellation diagram of the QAM. In the, if you see this constellation diagram of QAM, then we can see that all the symbols not lies on the circumference of the circle. It is inside of the circle or outside of the circle. That's why the phase as well as amplitude of the QAM is in QAM carrier is varies according to the input data. Okay, next, this is the block diagram of QAM, that is quadrature amplitude modulation or the quadrature amplitude shift keying. Okay, so the modulator or the transmitter of quadrature amplitude shift keying, we will see this with the help of this block diagram. So we will see one by one. So we have to apply the input binary data, that is B of t, as input signal to the serial to parallel converter. Then the serial to parallel converter convert that serial data into the digital parallel data. That is, if you consider, if n is equal to 4, then total number of symbols will be 16. According to that serial to parallel converter convert the serial data into the parallel data, that is B1, B2, B3, B4, like that, and that is applied as input signal to the digital to analog converter. So here we are using the two digital to analog converter. First one is the upper digital to analog converter and the second one is the lower digital to analog converter. Upper digital to analog converter takes the E1 bit and it will produces the staircase signal, that is E of t, and the lower digital to analog converter takes the negative bit and it will produces the staircase signal, that is AO of t. So that is the E1 bits is applied to the first multiplier. The upper one is the first multiplier and lower one is the second multiplier. So the first input to the upper multiplier was 1 bit. The first input for the second multiplier is the odd bit. So we have to apply the second input to the multiplier 1 and multiplier 2. So with the help of local oscillator, here the carrier signal is generated and that carrier signal is sin omega ct. That sin omega ct is applied as second input to the multiplier 1, and with the help of phase shifter, that is pi by 2, the sin omega ct will be converted to the cos omega ct, and that cos omega ct act as a carrier signal for the second multiplier, and that cos omega ct and O of t is applied to the second multiplier. So here for both the multiplier, upper multiplier, that is multiplier 1, and for the lower multiplier, that is multiplier 2, there are two inputs. That multiplier multiplies these two inputs and gives the output, and that output will be added with the help of the adder. Okay, so here with the help of this adder we'll get the output of quadrature amplitude modulation or the quadrature amplitude shift keying, that is S of t. S of t is equal to combination of output of two multipliers. So the output of QASK will be S of t is equal to A of t into sin omega ct plus A of t into cos omega ct. So in this way we will get the encoded signal in the modulator or the transmitter of quadrature amplitude modulation. Okay, then next is the receiver of quadrature amplitude modulation. For the number of symbols m is equal to 16 means number of bits small n is equal to 4, and here to get the original signal back we have to use the receiver of quadrature amplitude modulation. In the receiver of quadrature amplitude modulation we have to apply the encoded signal, that is S of t, in the modulator or in the transmitter as the input signal for the receiver of quadrature amplitude modulation. So here S of t is equal to A E of t into sin omega ct plus A of t into cos omega ct is applied as input signal to that particular receiver. So in the receiver block diagram, first block is consist of fourth raised power. So with the help of that fourth raised power, the input signal, that is S of t, that is encoded signal, is applied as input signal, that converted to the fourth power, and means cos raised to 4 omega ct plus sin raised to 4 omega ct. Then output of that fourth raised power device is applied to the band pass filter, and again we know that the use of band pass filter, the band pass filter is used to pass the band of specific frequency. So here we have to use the band pass filter of frequency, that is carrier frequency fc is equal to 4 omega ct. So with the help of that band pass filter, the output of band pass filter will be sin 4 omega ct plus cos 4 omega ct, because it will pass the frequency of 4 omega ct only. So the output of that band pass filter will be applied to the frequency divider, that is frequency we have to use here the frequency divider of divide by 4. So again the frequency divider output will be cos omega ct plus sin omega ct. So that cos omega ct is act as a carrier signal and it is given to the multiplier 1. Then sin omega ct is output given to the multiplier 2. The multiplier 1 is consist in the correlator 1. In correlator 1 multiplier 1 and integrator 1 will be there. In correlator 2 multiplier and integrator 2 will be there. The integrator 1 limits varies from 0 to n into tb. The correlator 2 consists of integrator 2 and its limit will be varies from 0 to n into tb. Okay, so that multiplier 1 multiplier of t is the encoded in signal applied as input signal to the multiplier 1 S of t and carrier signal cos omega ct, and with the help of that multiplier the output of multiplier is applied to the integrator 1. Then integrator 1 output is applied to the analog to digital converter, that is upper analog to digital converter, and same for the second multiplier. So second multiplier, here multiply the signal S of t and the sin omega ct, and then output of multiplier of 2 will be applied to the integrator 2, and here integrator 2 output is applied to the lower analog to digital converter. Actually here lower is there, lower analog to digital converter. Then again that analog to digital converter upper and lower will be convert the staircase signal into the digital signal. Okay, and upper is used for the even bit, lower is used for the odd bit, and again that 4-bit parallel to serial converter used to convert that parallel digital bit into the serial digital bit. So with the help of that parallel to serial converter, that output of ADC will be converted, it is in parallel form, and that will be converted to the serial form. And in this way at the output side of receiver we will get the original signal, that is binary data b of t, as record signal or the received signal at the output of receiver of quadrature amplitude modulation. Okay, so this is the operation of quadrature amplitude modulation of receiver. So in the next part we will see the next point. Thank you.